One of the first jobs I worked was a retail position selling merchandise at a theme park. It could be tiring, it was minimum wage, but selling non-essential goods at a theme park meant that I didn't deal much with crabby customers. All things considered, I liked the job, and the job liked me enough to offer me a promotion to team lead, which I declined because school was resuming and I was quitting. The part that bothered me the most, however, was that at the end of every day, every till was audited. Makes sense? You don't want your employees skimming something off the top? What bothered me was that each person had to have their own till, but it could really drag on counting all the money out by hand. It also had second order effects, such as limiting employee movement across the 5 or 6 different shops within our unit, which in turn made break coordination a total mess. Being the same math nerd then that I am now, I started thinking, what if you didn't need to give everyone their own till? What if instead people shared tills, and at the end of the shift, there was an audit of all tills across all workers to figure out if anyone was consistently miscounting over the course of several days, weeks, or months. You'd have more equations, one per till shift, than unknowns, one per employee. But you can use that data to infer who's off. In other words, you're solving an overdetermined system. A system of equations where there's more information than strictly necessary. Today we're going to learn how tools from linear algebra can not only solve overdetermined systems, but help answer real-world questions, like who's bad at counting change? To get started, we need to come up with a model. We let the variable xi denote the typical error rate, positive or negative, associated with employee I, and let bj denote the absolute error recorded for till day j, the error observed from a single till at the end of a day. For now, we'll define aij equal to 1 if employee I worked on till day j, and 0 otherwise, but later we consider an alternative. The system of equations is the sum of I of aji times xi is equal to bj. This can more often be written out in matrix form ax equals b. Now just to recap some basic linear algebra, linear equations like this can have 0, 1, or infinitely many solutions, and that number often depends on the number of employees, or variables, relative to the number of tildes, or equations. Here we usually have more equations, or tildes, than unknowns, employees, which means the system is overdetermined. Typically, such systems have no exact solutions, but we can still look for the best approximate one. When there is no exact solution, we look for the one that minimizes error. There are many forms of error, and here we'll use the square Euclidean norm of the residual. This leads us to the least squares solution, a core tool in applied linear algebra. The first step is to form the normal equations. The idea behind normal equations is instead of finding where ax minus b is equal to 0, is to instead multiply the system by A transpose, which reduces the number of equations from the large and overdetermined n to the much smaller and probably determined n. Defining the matrix S equals A transpose A and the vector C equals A transpose B, we get a new linear system. Sx equals C. This matrix S is guaranteed to be symmetric, and because the entries of A are non-negative and generally unstructured, assuming employee scheduling mixes people around, we expect S to be positive definite. And that's good, because it means we can use an array of powerful numerical tools to solve this system efficiently and stably. While we expect positive definiteness, we can at least guarantee that it will be positive semi-definite, which still opens up a number of possibilities. Another nice thing about the normal equations is that it reduces the system size, now equal to the number of employees. This is going to dramatically reduce the amount of computation needed, especially as the number of tildes increases every day, in contrast to employee turnover, which hopefully happens on a scale of months or years. Once we have our system ax equals b or sx equals c, we have several options for solving it. The first is to just invert s. Now this expression defines the Penrose pseudo-inverse A+, and yields the unique minimum norm least squares solution. It's elegant, but forming A transpose A can introduce numerical instability, especially if A is ill-conditioned. Other methods, like an SVD, are used to mimic this. The next solution we consider is the conjugate gradient solution. For large, sparse systems, iterative methods like the conjugate gradient become essential. It is designed for symmetric, positive, semi-definite systems like Sx equals C, and iteratively refines an initial guess until it converges. With a change of basis known as a preconditioner, it can solve problems involving thousands or even millions of variables with remarkable efficiency. Unfortunately, the normal equations are much smaller and quite dense, but this iterative idea will come up again, so it is worth mentioning at the outset. The next big idea is that since S is typically symmetric positive definite, we can factor S into L transpose, where L is lower triangular. This is called the Cholesky decomposition. Triangular matrices like L are great linear systems, since you can start with the smallest equation in the triangle and systematically solve for larger and larger equations in the triangle in a method known as forward or backward substitution. This lets us solve Sx equals C efficiently. Now this next method in theory works for either the original equation or for the normal equations, and that is the singular value decomposition, or SVD. It breaks the matrix up into three simpler matrices, U, sigma, and V, such that all three are easy to invert by either orthonormality or by being diagonal. In particular, we compute the compact SVD, which throws away everything in the null space. It is a stable algorithm that works for this problem and has a bajillion other applications in fields like machine learning, but it is rather expensive. The next method we consider avoids forming the normal equations altogether by instead decomposing A into Q and R, where Q is orthonormal and R is an upper triangular matrix. We can reduce the system to Rx equals Q transpose B, which is much easier to solve because R is also triangular. The QR factorization is more stable than the normal equations are, and more efficient than the SVD for most practical cases, so this would be a strong contender for a best solver. However, the strongest contender is probably the LSQR, or the least squares QR, which combines the iterative approach of the conjugate gradient method that I mentioned earlier, with a bunch of smaller QR factorizations to arrive at the similar solution much faster. This requires no A transpose A, nor does it require the expensive SVD. Before I conclude, there is one modification to the problem that might improve it even further. Instead of simply tracking who worked on what till during what shift, a login system could track who sold how much on a given till for a given shift, and then weigh the system by the amount sold. This would increase the chance that S is symmetric positive definite, but it also means that the variables are now dimensionless. If that word dimensionless means nothing to you, check out my latest meme stream, where I talk about the importance of dimensions as a key tool to mathematical modeling. Finally, if you want to implement solvers like this one discussed in the video, I would say for most non-researchers it's worth doing once, so that you understand the algorithm, but then using open source or closed source libraries that are already out there, since these have been optimized for decades to squeeze out just a little bit more from the previous version. So what does all of this mean in our retail setting? Rather than assign each employee a personal till, we could allow shared tills and use this data to solve for individual error patterns. The vector x gives us a best fit explanation of the discrepancies across all till days. If an entry in x is consistently large in magnitude, that may indicate someone is systematically miscounting change, however you can't determine motive. But you can at least know who to approach, and say something like, "Hey champ, I noticed that you're doing an awful lot of miscounting.
Are you stealing from the company?"
This strategy doesn't replace supervision, but it makes it more efficient with inference. It allows flexibility in scheduling and reduces logistical friction without sacrificing accountability. With enough data, the linear system acts as a kind of audit trail, letting us flag suspicious patterns without needing rigid one-to-one till adjustments. Sometimes, the best solution isn't to control a system more tightly, you just need more equations. This example might seem specific, but it's one instance in a broader pattern. Overdetermined systems show up everywhere. In data fitting, sensor fusion, imagery construction, every kind of machine learning algorithm, linear algebra gives us a powerful toolkit for transforming noisy, inconsistent information into reliable answers. The one sad part about this example is that cash is no longer used at a number of in-person stores. But if you've ever worked behind a cash register, let me know if this was a problem for you. Or if you have horror stories from that job, I would love to hear those too. If you like this video, then like this video. Thank you for watching.